Okay, good. Getting started. Learn about Leap and QC, run a demo, get set up, install it. Okay. Learn about Leap, watch videos, meet DWave customers, and access research publications. That could be interesting. Maybe let's just jump through the demo. Experiment on a quantum computer. Factoring, social network analysis, quantum material simulation. Okay. Showcase different types of problems. The DWave. Let's do the. I mean, I know that's that's an interesting one because it's basically what is believed to be one of the dangers of current encryption. So if we're able to basically factor really big numbers, we're literally able to, um, you know, basically break any of the existing encryption protocols. So demo one, let's see what happens. Factoring by running a multiplication circuit in reverse. Integer factoring is the process of finding factors that when multiplied together give a target integer. I know that, that's basic stuff, good. Because factoring large numbers can be extremely time consuming, it is the basis of, as I said, right, so it's the basis of the RSA algorithm, the most widely used public key cryptography system. Good, so let's continue. Choose a number to factor. I like the way this is built. I think it's pretty intuitive. Okay, so let's see. 21. Continue. How classical computers factor. Classical computers are inefficient at factoring. For small numbers, a basic approach like trivial division, in which we methodically try dividing our number by candidate factors, is trivial. Yeah. So it would take months for a 512-bit and over 1,000 years, and then like just million years for like 1,024-bit factoring. So I guess and that's the idea why it's used for encryption. Okay, so good. That's a classical way, and so okay, that's how you would implement that in a classical computer. So with Boolean operators and ORs and all that stuff. It can be difficult classically. It is easy to check the results. Yeah. Okay. So in binary 3 and binary 7, and then get 21. So that's a multiplication. Sorry, that's a multiplication circuit. I understand that now. Okay, so it's not the factoring yet. That's how you multiply the numbers. Let's move forward. Multiplication is an example of a more general Boolean logic circuit formed by interconnected Boolean logic gates. Half adder, full adder. I mean, I remember that from when I was studying computer science. You know, you can build a half adder and a full adder with all this kind of stuff, basically just with the different logic gates. So formulating the problem from a constraint satisfaction perspective eliminates directionally from the relationships, making it possible to run circuit in reverse. Okay. So basically, you formulate the problem of multiplication as a constraint satisfaction perspective. So, and that allows you to reverse that. Let's see. It is not obvious. What do they mean by that? I mean, constraint satisfaction problem, that's sort of a standard, sort of a way you can reformulate problems, so then you can apply existing methods to solve them. But I'm not familiar with that right now, or I don't have that on the top of my head. So, okay, I mean, it's still quite not so much to read, but it's a bit dense. So a constraint satisfaction problem can be programmed into the quantum computer one logic gate at a time. Shown here, an AND gate is a constraint between two binary inputs, so one and one output. It outputs 1 only when both binary inputs are 1. Yeah, that's the definition of an AND gate. Binary constraints can be mapped to a set of qubits, quantum bits, and couplers, connectors. There's a lot of new stuff in here, so that those qubits associated with the constrained inputs and outputs will, with high probability, find values constant with the constraint. So now I know a little bit about quantum computing already. The thing is, yeah, okay, maybe they assume you've gone through the basic videos before jumping into the demos, right? But people, I mean, I'm eager to try stuff, so that's why I jumped in the demo. And if you really don't know anything about quantum computing, you're going to be confused by these. For the AND gate, for the AND gate, the qubit associated with the output seeks a value of 1, even only if the qubits associated with the inputs are all setting into a value of 1. Otherwise, it seeks a value of 0. Yeah. Quantum computer, qubits and couplers. ABC. Next, creating the mapping. Let's see. So applying transformations across all the gates in the circuit creates the mapping to qubits and couplers. Oh, okay. So basically, that's okay. So they basically replacing the gates by the classical gates by however they specify quantum gates. So this triangle here is what we saw in the previous step. And I guess those are then the equivalents of the other gates, the half adders and the full adders, I guess. While it's possible to create wires in the quantum computer matching the interconnections in the circuit, the problem mapping is more efficient if the number and length of wires is minimized. A set of interconnected inputs and outputs is reduced to a single qubit rather than distributing the information across several wires. Click qubits to the right to see the final transformation. A set of interconnected inputs and outputs. Okay, so then each of those things will be transformed in qubits. What the okay. Okay, that was a big jump right now. So what happened? Okay, so basically connected it just connects the nodes, right? So for example, this is connected to this one. What happens when you do that? Yeah, so okay. So basically they remove the wiring from the diagram and then they just connect everything the way it was connected through the wires. That's all confusing. I mean, if you're, okay, so far I'm confused. You have more information. What happens when I click here? Okay, so calculating energies to find the best solution. To understand how to express a problem in a form that the DWave system can solve, we must first develop an objective function, which is a mathematical expression of the energy of a system as a function of the binary variables. In most cases, the lower the energy of the objective function, the better the solution. Sometimes any low energy state is an acceptable solution to the original problem. You see, that's what I meant. So D-Wave guys use a bit of a different approach than the IBM guys. So here's about the energy, literally the energy levels. The thing is, you have to transform your problem for this to work in your hardware. You have to transform the problem in a way that you can use the properties of that quantum computer, which is okay. I mean, I guess for an early stage thing, it's okay. But if we want to build up intuition, at some point I'd love to see something that is a bit more abstract from the hardware itself. But it might not be possible. We'll see. Because the idea here is that, you know, the idea behind quantum computing is that you can, as far as I understand, right? So it's basically you use quantum physics properties to solve problems. So you sort of use, I don't want to sound too kind of clickbait type of thing, but you use nature's own physics to actually solve problems or process information, which at the end of the day is what you do with a classical computer, right? So it's just ones and zeros, and I mean there's like transistors behind that, and then if there's electricity up to a certain level, then it's one, and if not, it's zero. But here's a bit more complex. Okay, so solution space, I get it. So yeah, this is definitely a lot of information. When defining a problem, we change the bias weights for the variables and the relationship between them such that the best answers are favored and non-optimal solutions are penalized. Energy calculation for an AND gate given the following energy E function. So, okay, inputs and outputs. So you've got 0, 0, 0. Yeah, so that's basically the AND gate, right? So it only outputs 1. It's kind of weird. Yeah, okay, but we don't want, so it basically says the 4 valid states have the lowest energy, so they are the most likely solutions. But that's not correct, right? So, I mean, okay, that's correct, as in if you take in the output as well, yeah, 0 and 1, it's 0. Oh, okay. So that's more than that. I see. So that's the function. Hmm. An equivalent calculation can be applied to the half additive and full additive in orbital. So you basically come up with an energy equation that encodes the logic in a way that the lowest energy points are the ones you want to get at, right? Um, so instead of being really, Boolean in the sense of true and false, it's a bit more probabilistic, um, because at the end of the day, you could get any of the points in your solution space, so to say, or any of the energy levels, but you will get the lowest levels with the highest probability. Okay. ABC. Okay, so basically when you do that, right, so if A and B are 0, and you calculate that, right, and C and 1, then you're going to get energy 6, which is good because it's high energy, so it's not a valid combination. Okay, I get it. I get it. Yeah, but then it's tricky to come up with such things, right? I mean, you must have either sort of there's probably already a catalog of the basic things you can build in terms of the basic equivalent of classic gates. Okay, yeah, okay, not that bad. And then there's a similar you can do for the half others and the full others. Continue. So run it on our quantum computer. Okay. The binary values on the output of the multiplication circuit can be fixed to the number we want to factor. The quantum computer returns the values of the remaining variables, including the factors we seek. When we formulate a problem in this way, we are specifying the relationships among variables. This approach can be used to represent any Boolean logic and find solutions to a large set of constraint satisfaction problems. Interesting. So, okay, so that's 20. That's 21, right? Okay, but can I just run? Okay, I'm gonna run. So that's 21 in binary. What we don't know is what's happening in between. It's just it's like I get it that each of those things encode energy functions, but then it's a bit of a magic thing still happening. So if I run that, oh no way, that's nice. Okay, I mean, uh, I guess we'll come back later. It's just a pity. Um, I kind of like was, it's still really low level, but more or less, I'm understanding what this really means. It's just a lot of questions still in between. What's happening in between here, right? But so yeah, it's a pity. That's sad. That's sad. Congratulations. How's that? Congratulations. Continue. I can't either continue because I just can't run that. Okay. Okay, let me close that.